So we're going to start talking about circular motion today, okay? Because we just finished up dynamics before you guys went on break, which I'm sure you remember really well, right? You guys all remember dynamics. Let's go over Newton's 3 laws real quick. What's the first one?
Inertia.
Which means?
An object at rest will stay at rest until an object in motion acts upon it.
An object at rest will stay at rest, and an object in motion will stay in motion until acted on by an outside force. Okay? What's the second law? Yes, force equals mass times acceleration. What's the third law? Every action has an equal and opposite reaction. I like how that's the one that everybody remembers. Okay, so taking that knowledge, we are going to try and apply it to things that are moving circularly. That's a word, okay? So circular motion. Now, when we're going to do that, the first thing we need to talk about is that when we have a circle and things are moving in circular motion, that Donald needs to put away his phone, and that the way things move is that we're going to want to look at them as they occur at a point. So here are 3 points that something might be during the path, right? Now, our velocity, what do you think that is since I drew a straight line?
Tangent.
It's tangential, okay? So we are going to have a tangential velocity. Okay? And the acceleration of objects, if this is the center of the circle, acceleration always points towards the center of the circle. And of course, every circle has a, what's the R represent? Radius. Every circle is going to have a radius, okay? Now, like we just said, the particle's velocity is what to the circle? Tangential. It's acceleration, which we call a centripetal acceleration. Always points towards the center of the circle. Do you have that like beam to your heads now since I've said it so many times? Yeah? It's really in there? Okay, good. Now, the particle can also have something that we call angular velocity, okay? Angular velocity is not going to be tangential. It's the velocity of it going all the way around. And how we represent angular velocity is with this little W. Oh God, it's a Greek letter. I don't remember. It's a whoa. It's a whoa.
No, it's oh God.
Okay. And this is angular. Sure, call it a whoa. Angular velocity, okay? That's our angular velocity. And how we represent our tangential velocity is that it's actually equal to that angular velocity times the radius of the circle. Okay, so we're going to take angular velocity, multiply it by the radius of the circle, and that will give us our tangential velocity. Okay? And then you might be wondering, well, you gave me an equation for this. What's my equation for acceleration? Okay? The equation for acceleration is going to be that velocity squared over r, which you can also write as, I'm pretty sure this is actually an omega. Omega squared r. Or whoa squared r.
No, omega is a different.
Omega looks different?
Yeah.
Somebody find out what that is.
Lowercase omega.
I think it's lowercase omega. I do, but I could be completely wrong. I do not remember. I'm just like, that represents it. Okay. So while you're looking at this, though, yes, I'm right, you guys. Take that. Whoever said I was wrong, was it you? I was right. Okay, now when you look at this, do you think our usual XY plane is going to work when we do these problems? No, it's not going to work, okay? So, the planes, you guys, we're going to use a brand new coordinate system. I know that, does that excite you? Woo! Okay, so our coordinate system, I'm going to represent with the blue here. We're going to have our T, and then pointing out is the Z axis. So I'll put pointing out of board is going to be our Z axis. So the Z axis is trying to come out and slap you or something. Okay, that's what the Z axis is doing. It's out of the page, out of the board. So when we're talking about particles moving with circular motion, okay, if you read a question and it mentions an origin, yes.
Is R for the axis reference to the radius?
Mm-hmm.
Then what would T be reference to?
So T is, yeah, the tangential.
Oh,
Mm-hmm. You're so smart. I know, but still, you know, good job. Let me compliment you. Okay? You're welcome. All right. And when you hear about an origin is going to be where the particle is located. So this would be an origin at some time. This would be the origin at another time. This would be the origin at another time. And so on and so forth. Wherever the particle is located at that point in time is what we're going to consider our origin point. The R-axis will always be from the origin to the what? Center of the circle, okay? The T-axis, or as Ian so smartly said, the tangential axis, is tangent to the circle. And it's going to point in the counterclockwise direction, okay? Do you guys notice how with each of these vectors I drew, it's counterclockwise? Yeah? Okay, so that's always how that one's going to be. And the Z-axis is considered perpendicular to the plane of motion, which if it's moving this way and the Z-axis is pointing out at you, doesn't it make sense that that's perpendicular? Yeah, it'll make more sense when we start drawing more pictures, okay, you guys? So what we call this is the RTZ coordinate system. Woo, RTZ coordinate system. So what we're going to do now is we're going to go over the components of velocity and acceleration for each of the coordinate systems. And when you see this, you're going to be so happy because you know how I always say that like our favorite thing in physics is when things equal zero. So many of these things equal zero. Okay, it's really nice. It makes the math a lot easier and you know where to go. So let's start out with all of the V's. So we would have the velocity in the R, the velocity in the T, and the velocity in the Z. If you had to guess, which one of these, or which multiples of these do you think are equal to zero? You had to guess. Z, yep, Z is going to be equal to zero. Is anything else going to be equal to zero? No. R. T is the only one that we have a value for. And our value for the velocity in that tangential axis is that omega times R. So now,
So the reason why
uh-huh,
the velocity of the radius is 0 is because it's always
tangential.
The origin is always on the point,
Mhm.
like the object.
Yep.
And if it wasn't, it would actually have motion towards the center, probably.
Yeah, but then what would you be doing if
Yeah,
you're,
you'd just be doing a traditional.
yeah, you'd just be doing a traditional problem. It
Alright.
wouldn't be circular motion. Okay, which one of the accelerations do you think are 0? Which ones?
T and Z.
Yeah, T and Z are both going to be 0. Okay, because when we drew our picture, acceleration was always doing what?
Going towards the center.
Going towards the center, so it only exists in the
R.
radial, right? Good job, it only exists in the radial. And that, like we looked at earlier too, is going to be either v squared over r, which is also the same as saying omega squared times r. So our velocity only exists in one plane, and our acceleration only exists in one plane, and they're different planes. So do you see how this is probably going to end up making our math a lot easier than it would be otherwise? Yeah? Awesome. Now,
Why does radius have acceleration but no velocity?
okay, because the velocity is always tangent. So it doesn't go towards the radius.
Oh, okay.
Mhm.
That makes sense.
And as far as angular velocity is concerned, just to go ahead and introduce you to this, we'll talk about it more in depth later. This is, shout out to Donald since he loves calculus, is represented by d theta over dt, d theta dt. And our units for omega, or angular velocity, are going to be radians per second. Okay, so that's our new unit. We have radians per second for omega, aka angular velocity. So far, so good? Yeah? And do you see how the theta over t shows us it's radians per second? Yeah? Awesome. Well, then let's keep trucking. How's this feeling to you guys so far? Not bad. Good. Good. Okay. So, question. A particle in uniform circular motion, all right? It's just going around pretty constant. Do you think it travels at a constant velocity in a straight line?
No.
No, because it's in what kind of motion? Circular motion. So, is there constant velocity there? No, because even if it's constant speed, what's changing about it that makes the velocity not constant?
Orientation.
The direction. Okay, the direction. Now, according to Newton's first law, though, there has to be some sort of force that's acting on this particle in order to keep it moving and to change. Because if velocity is changing with direction, is acceleration also changing? Yeah. So if acceleration's changing, that means that there's force, right? Because it's mass times acceleration. And acceleration, if it's changing, it's not 0, right? So we're not going to have an acceleration of 0. So there has to be a net force on it. And Newton's second law, as you guys so confidently told me earlier, is that force is equal to mass times acceleration. And didn't we just find out how we write acceleration for circular motion? So force is going to be equal to mass times acceleration, which is the same as saying it's mass times v squared over r, or mass omega squared r.
Oh, okay. So that kind of answers my question earlier. With, like, why does like the radius or like the velocity radius 0, but the acceleration radius isn't?
Mm-hmm.
Acceleration can't be 0, otherwise it would be flying out.
Yeah. Otherwise, it would just go.
Okay, and if it was like if it did have velocity, that would imply that it was getting closer or further away from the center, which wouldn't be happening in most situations.
Yeah, it's not going to happen. It's going to stay a constant distance from the center. Because it's a circle. So the particle of mass m does move at a constant speed around the circle of the radius. But since it's not a constant velocity or a constant acceleration, we're still going to have some sort of force. So what that's going to look like, if we draw our pretty little circle, is that for every place or origin that our particle is at, there will of course be some sort of tangential velocity with a constant speed, and then F net is also going to be pointing towards the center. Okay, so at all points, F net will point towards the center. Now, why does that make sense? That F net's going to point towards the center. Exactly. It's equal to mass times acceleration, and acceleration is always pointing towards the center of the circle. So our net force is always going to point towards the center of our circle. Now, you know how we, huh?
That's because it's the only place that has acceleration, right?
Yep.
Okay.
You guys are so proud. So, you know how we listed out all of the velocities and accelerations in all three planes? Okay, now we're going to do the same thing for forces, just so we can have a visual, okay? So we're going to have the net force in the R, the net force in the T, and the net force in the Z. So remember, when we do net force, we take out and we do our little fancy summation signs, okay? So for instance, the F net of the R would be the summation of all of the forces in the R. The T would be the summation of all of the forces in the T. And the Z would be the summation of all of the forces in the Z direction, or the Z plane. Now, we also know that F equals MA. So it would be MAR, MAT, and MAZ. And looking at this, we realize that are a few things up there going to be equal to 0?
Yeah.
Thank goodness. What's going to be equal to 0? F net T is 0, and F net Z is 0. And what about F net R? What's that going to be? M times what?
M times omega squared.
Also, how else can we write it?
M times B squared over R or just MA.
Yep. So all three of these forms are basically acceptable, as long as you make sure you have that subscript with the A, okay? Still so far so good? Yeah? All right, then I feel like we are ready to get into our first example together. Okay? Not too bad, right? No. And this is uniform circular motion. Uniform circular motion is nice. Do you think we do ununiform circular motion? Yeah, we do. That one's still fun. It's just like,
Is there different equations though? Like different.
you'll have to wait and see. Who knows?
What?
Okay, so this is called spinning in a circle. And don't worry, you guys, these notes have already been posted for you in Google Classroom. So when I read this description out loud, it is available for you online, okay? So you're not going to have to be like, I don't remember what I did math with. So it says an energetic father places his 20-kilogram child on a 5-kilogram cart. Okay, so let's start with that. We've got a kid who is sitting in a cart. His hands are up. He's having fun.
He's gonna fly out.
Okay? He is 20 kilograms, and the cart is 5.0 kilograms. All right, so this is what the info we have so far. To which a 2-meter-long rope is attached. All right, we've got a 2-meter-long rope attached. Okay. He then holds the end of the rope and spins the cart and the child around in a circle. Okay, so now the dad is like close to the ground. He's holding this with really, really long arms. He's going to spin his kid around in a circle. It's not a very good circle. It's very lopsided. That's more like an ellipses. Hold on, you guys don't want to learn the math for an ellipses yet. It's not. Yeah. That's still not a very good circle, but it'll do, okay? So, keeping the rope parallel to the ground, as we see here. If the tension in the rope is 100 newtons, we want to know how many revolutions per minute does the cart make. And thankfully, we're told that the rolling friction between the cart's wheels and the ground, we can ignore it. It's negligible, okay? It's like it's not really there. So we want to know how many RPMs, how many revolutions per minute. So we've got one picture here so far. And what do I say you should draw when you're doing something that includes Newton's laws or forces? What kind of picture are you supposed to draw? Free body diagram. Okay, so we're going to say this is our child. And our child is our particle, right? Yeah, it's going to be our origin at all points along this. So this is our kid. And what forces do we have acting on him? Okay, so that's what kind of force is that called? Tension. So there's some sort of tension acting on the kid. Right now, the kid's over here. We're going to say, because at any point, tension's acting on him. So we can really draw that in any direction we want. And I'm going to draw it in the positive direction just to make our lives easier. Okay? What else is acting on him? If he's on the ground. Yeah, we got the force of gravity. Force of gravity always acts which direction? Down. Okay, and then what's the one other thing we got acting on him? Normal force. Good job. Okay. So this is everything we have acting on our kid. So now that I have this picture, I don't know, I feel like we might not need this one as much. But first, let's go ahead and make sure we have all those values written down somewhere in this handy dandy knowns column. Okay, so what is the overall mass of our particle that we're dealing with? 25 kilograms. How'd you come to 25? Yep, you're going to add the kid in the cart. All right, what is our radius of this circle? 2.0 meters. And then what is the tension here? 100 newtons. What were we asked to find?
Revolutions per minute.
Revolutions per minute. So that's going to be omega, or angular velocity. So we want to know what that is in revolutions per minute. So you know how we said it's usually going to be represented in radians per second? Well, this is just like when we say, well, mass is usually represented in kilograms, but maybe a problem will ask you for it in pounds. Sort of the same idea. You can convert back and forth, okay? So far, so good? Yeah? Awesome. Then I'm going to erase this picture of this child swishing his child around so that we can do some math. All right. Let's start by summing our forces in the R direction. Okay. What forces do we have in the R direction? In the R plane? Tension. Is there anything else?
Acceleration.
Was that on the board represented? That's roped into the acceleration, into the tension, right? Because this is going to be equal to m v squared over r. Or, you know, m omega squared r, but do we have omega? No, we don't have that, okay? And then, do we have anything in the t-plane right now that we're dealing with? Any forces on this picture? No. So what plane, what's the other plane we have? Yeah, the z-plane, okay? So what forces are in the z-plane? Huh? We got two.
Yeah.
Gravity and the normal force. So you guys so very smartly realize that this is our Z and this is our R. Okay? And what do you think that equals? 0. Because normal force is equal to the force of gravity, which is equal to m times g. You guys didn't lose everything over break. I'm proud of you. Good job. I would have. Okay, now I heard you guys talking about acceleration, so let's just go ahead and make a note of that too. What do you think acceleration is in the R? What do we say acceleration is in the R direction? No, it's the v squared over r, or omega squared r. And what's it going to be in the z direction? 0, right? We only have acceleration in the r. Okay. So are we still good so far? Yeah? You promise? You need to get more sleep. You can do it. I believe in you. Okay. So we're going to take this that we have right here. Okay? That's what we're going to focus on. I'm going to get rid of this right now just so I have more room to do math. So we know that T equals m v squared over r, right? Yeah? So how do we rearrange? I want to know what v is. Because I know T, I know m, I know r. I want to find what v is right now. So who can tell me how to find v? How do I rearrange this equation?
TR
Okay.
divided by M.
So T, what?
TR divided by M.
TR divided by m. Does everybody agree with that?
Squared. Right. Square root
Equals
equals
v, right? Okay, so let's see what we got here. We know that T is 100 newtons. We know that R is, what's R? 2 meters. And what's our m? Okay, so who can tell me what our velocity is? Can you give me a decimal? Huh? No.
That's 2.83.
Yes. What are the units?
RPM.
This is velocity.
Oh, you lost.
Yeah, okay. So we found velocity. Now we want angular velocity. Okay? And remember that we said omega is equal to v divided by r, right? Somewhere back in your notes previously. Okay? So we just found our v, which is 2.83 meters per second. And what's our r? 2 meters. So who can tell me what our angular velocity is here?
1.42.
Did everybody else get 1.42? Yeah? What are the units? We're not at RPM yet. What do we always get as our base units?
Radians per second.
Yes, radians per second, but we want it in RPMs, right?
So don't you just multiply by 180 over pi?
I mean, you don't even have to do that. So how I would show you to do it, how I like to do it, is I go 1.42 radians in 1 second times, we want, what do we want? Do we want revolutions per minute, right?
Yeah.
So in 1 revolution of a circle, how many radians are in 1 revolution of a circle?
2 pi.
2 pi. And then how many seconds are in a minute? All right, tell me how many RPMs?
I got 133 points.
Ooh, no.
Wait, yeah.
That'd be really fast. That kid would be like dead. Are you laughing at a dead child?
No, kidding. Passed out. Experiencing like 14 beats.
13.56.
That sounds good to me.
Wait, how did you guys get that?
Yeah.
I got the. Well, oh wait, you did something.
Oh,
You did the 2 pi.
hey, we need to be in radians.
No, how
You
does
be
it
in
read?
radians.
Oh,
I don't think we use radians.
do we?
No.
Well, we're using radians. It doesn't need to be a
It
radian.
just doesn't need to be radian mode in your calculator right now.
Wait. Radian mode doesn't change how like basic math works. It just changes
Okay, I have
all
no
the,
idea.
changes between them. I'm gonna solve it. Yeah.
Who's a
How
good
did you
team?
get 13.56?
Let me see.
Like, I put that in my calculator.
Give me.
I got 2.087.
That's wrong.
I don't know how I did that.
So
It should be really close to 14. Good guess.
okay.
What'd you get, Daniel?
You have to put it in the front. Well, you have to do it like a.
You what?
I don't want. Like, you have to write it as a front. You can't like do. I just did
Oh god, this isn't the last example today, you guys.
Yeah.
Wait, so you have to put it in a fraction?
Yeah, you have to look at it exactly
Like, because what I did 1.42 times 60, and then
Talking about how to get the answer on your calculator takes more time than it takes for me to go over the problem.
Use 3 days. Like use 3 components. It's
Are we there yet? Are we there? Yeah, we're there. Okay.
Let's do 1.2.
I know you guys, calculators are hard.
So I know if you wanted to like correct it, you say see how you divide it.
All right, you guys, shush. I want to tell you something cool about the problem we just did. Okay? The problem we just did is a representation of something that we call the central force model. Okay? Now, what that is it means it's a force that is always directed towards the same point. So the tension in the example is considered a central force. So is the gravitational force. That would be like acting on a satellite or something like that, because that's sort of what keeps the satellite going. Okay, so it's called a central force. Now, we'll start the next problem, but we might have to finish it tomorrow, okay? This one is called Turning the Corner, Part 1. There are 2 parts. That's so exciting. Whoever knew there was so much that went into turning a corner. Okay, so we've got a car, and I'm going to draw the view from like we're above the car. Okay, the car has wheels. I know this isn't the best above thing. And what they want to do is they want to turn the corner. Okay. Now, what we want to know is what is the maximum speed with which a 1,500 kilogram car, so I'll label that for you. Yeah. It doesn't go away. Can make a left turn around a curve of radius 50 meters. So this curve has a radius of 50 meters. Okay? On a level, unbanked road without sliding. Do you guys know what a banked road is? Yeah, it's where it's sort of like this, okay? It's like at an angle. This is unbanked. So it's going to be flat, okay? And we want it to not slide. So this is our picture. And we need to list out what our knowns are. What do we know?
What's the friction constant?
We'll get there. I'll give it to you. Okay, so what's the mass of the car?
1,500.
Yep. Okay, what is the radius of the circle? 50 meters. And then the big question that Ian just asked, he wanted the coefficient. Do you want the coefficient of static or kinetic?
Kinetic. It's moving. Yeah. Static.
Static, because you don't want it to
Move.
slide. Okay, and what that is it's going to be 1.0. Okay, it's going to be 1.0. And what we're trying to find is the maximum velocity that it can take this curve, okay? And what are the units for velocity? Meters per second, right, you guys? Yeah, meters per second. All right, so let's think about how to tackle this. I think what we should start out with is a what? Free body diagram. Okay, so I'm going to draw this dot. What do you think the dot represents?
The car.
The car. Okay, what do we have acting on the car?
Gravity.
Okay, we got gravity. Yeah, what else do we have acting on it?
Normal force.
We got normal force. Okay, what else is acting on it?
Acceleration. Or is it accelerating or is it moving on a constant?
Well, we're trying to find the maximum velocity you can take this turn with. But you know how we had tension on the last problem, pulling it towards the center?
Yeah.
What's pulling it towards the center this time?
Static friction.
Static friction.
How do you use static friction? Yeah.
I'll show you. I'm about to put the equation up here for you, okay?
Yeah, fun.
Yeah, it's fun.
That's going up.
All right, so remember, you guys, since we're talking about fun, that the maximum static friction is equal to mu s times n. So the coefficient times the normal force, because friction is fun.
F is in newtons, right?
Smacks.
Okay.
Because the coefficients of friction don't have units. So the only unit we have is for normal force, which is a newton. So the force of friction is going to be in newtons because it's a force. Okay, so let's look at summing some forces again then. Which force plane do you want to sum first? R, T, or Z? R, okay. What all do we have in the R direction? We have that static friction. Is there anything else?
No.
No, okay. And that's going to be equal to M times A, and what's A? V squared over R, right? That's how we represent it now? Yeah? Yeah? Okay, cool. Okay, and then what's the one other plane we have some forces in? T or Z?
Z.
Z, okay, what forces do we have in Z?
Normal force and gravity.
We've got normal force and gravity. So the force of gravity, normal force, that would be equal to mass times acceleration, and our acceleration in the Z is 0, 0. And don't forget that normal force is equal to that force of gravity. Never forget that, okay? It's going to help you out your whole life. Okay, super, super difficult math now, you guys.
Algebra.
Solve for V. Again, you guys should already know exactly what to do. It's going to be V equals
The square root of Fs times R over M.
Everybody see how you got that? Do we see? Do we see how you got it? Awesome. Okay. So, do we have everything we need to solve for that V? No, we don't. We don't have Fs yet. We don't know what it is yet.
You get it.
We can get it. Okay. So we said that this is true, right? You guys remember correctly, friction is fun, right? Friction is fun. So that means What could we sub in for the normal force?
Gravity times weight.
Gravity times mass. Because gravity times mass actually is what gives you weight. Okay? So if we take that, what should we probably do now? Those of you who got the right answer, come on, help me out.
Substitute that answer, or actually, just multiply the gravity times the mass, and that gives you the F of static friction. And then you put that into the
Okay, so what's the mass?
14,700. Oh wait, no.
What is G? Okay, and what was our coefficient of static friction?
1.
Okay, so what is our maximum static friction?
14,700.
Okay, it's 14,700, is that what you said?
Yeah.
What are the units?
Newton.
Newtons. Okay, where do I go from here?
You implement that into the equation for V that we did earlier.
Okay, yeah. So since we have Fs max now, that means that the equation now will give us the maximum velocity. So we're going to do the square root of what? What do we plug in?
Fs times R divided by
Okay, so we have Fs. What's R?
15 meters.
And what are we dividing it by?
Mass.
Mass. What's our mass?
1,500 kilograms. Pure steel.
Okay, what's our maximum velocity?
7 radical 10, which rounds to 22.14 meters per second.
Everybody good on that? Yeah. Those of you who went home and attempted it, even if you didn't get the right answer, I am proud of you for going home and actually attempting it. So good job. You listened to me. All right. If you want to read up on some interesting stuff about that, I have like a little asterisk at the bottom of the page that I posted that talks about sort of like what would happen if like different things were parallel to V or opposite and all that fun stuff. So it's pretty interesting read if any of you guys are interested. But now that was called basically turning the curve part 1, right? So now we're going to do part 2. So this was a flat road, correct? Well, we're going to do a banked road. So we're going to do a road that's at an angle. Okay? An angled, right? It's insane. Okay, so if it's at an angle, that means that the road is sort of like this, okay? So here is our car, the back of our car, and it's on a banked road now, okay? So we have got a highway curve, and this time the radius is 70 meters. So let's start our knowns. We got a radius of 70 meters, and the theta is 15 degrees, okay? So it's inclined at 15 degrees. We want to know at what speed, or we'll call it V naught, can a car take this curve without assistance from friction, okay? So we want to know what speed do we need to go at so that we don't need friction. Let's say maybe we don't live where we do. We don't live in Georgia, and the road is completely iced over, okay? And we've worn out our tires. The treads almost don't exist anymore. We're poor, maybe. We can't replace them. I mean, that's sort of where my husband was at when I met him. He had like no treads on his tires. It was sad. Okay, so we're going to be sliding, basically. We have no friction to help us stay on the road, okay? So we need to figure out how fast we need to go. So let's start out by drawing our free body diagram. Let's think about it. What forces do we have acting on this car? Gravity. We've always got our best friend gravity, right? Okay, what else? Normal force. Is it going to point straight up?
No, it's gonna be pointing at a 15-degree off.
Yeah, it's going to be pointing sort of like that. Okay? And then, well, we don't have any friction, right? But if we are rounding a banked curve, which way is our net force going to point?
Forward.
Towards the center. Good job.
Is that gonna be off of our point?
I'm just saying that in general, it's going to be pointed in that direction. Because technically, you guys, we don't have friction, so I'm not going to draw the actual force being attached to the particle. Okay? This is just saying that we know that our net force is going to need to be pointing towards the center of the circle. Okay? All right. So let's think about this. Now, previously, wasn't N always on the z-axis? Yeah. Is it only on the z-axis now? What other axis is it in? R. Okay, so we're actually going to have an R component of our normal force now. So let's think about our R component of our normal force. What do you think it's going to be equal to? Like, is it going to be in sine theta? Is it going to be in cosine theta? What do you think?
Oh, it's gonna be the X.
Why is it sine? Because what? Yeah. So this is our X. And this is our Z, and this would be our R. Okay? This is what we're doing here. It's going to be in sine theta. Now, let's see here. What areas should we sum the forces in? Like, should we be summing them in the T, in the Z, in the R? What should we be doing? The R and the Z. Which one do you guys want to start with, R or Z?
R.
Okay, let's start with R. So if we are summing our forces in that R plane, what are our forces in the R plane? In what? In sine theta, right? Because that's what we just said that that's equivalent to. Now, is there anything else in the R plane? No, there's not. Okay, so this would be equal to MAR, right? Which is the same as MV squared over R. So that's our summation of all the forces in the R direction, okay? Because obviously it's not going to be zero, right? Because which way is the F net pointing in? Which plane? The R plane, right? So we're not going to have it equal to zero. If we had it equal to zero, there would be no net force, okay? So which one do we need to sum now? The Z, okay? So when we're summing in the Z plane, what forces do we have in the Z plane?
Gravity and normal.
Yeah, we've got gravity and normal, okay? Well, what is our normal though? How do we represent it? Are you sure it's in sine theta? Because in sine theta gives our R. Yeah, it's going to be in cosine theta. And then we've got the force of gravity, right? So I'm just going to go ahead and represent that as minus mg, okay? Because we know it's in the negative direction, right? And we know that it's equivalent to mass times gravity, or that acceleration due to gravity. Okay, now what's this going to be equal to? It's our favorite number. Zero. This is going to be equal to zero. Because is our net force in the Z plane? No, it's not. So it's going to be equal to zero. All right, where do you guys think we need to go from here? We need to figure out what? What about the N? We don't have friction. Do we want to know what the normal force is? Yeah, because we already know what theta is, right? What's theta? 15 degrees, okay? But we don't know what n is. If we know what n is, we can solve for like a net force. We can sort of figure out a little bit more of what's going on in this problem, okay? So which one of these two are we going to be able to use to solve for n?
First one.
We can honestly use either one, but I agree with the second one's going to be easier, isn't it? Because do we have this? We don't know what that is. So can we really use the first one? If we had all the variables, we could, couldn't we? But we don't have them. So we're going to need to use this one right here. So if we write out n cosine theta minus mg equals 0, how do we rearrange to solve for n?
N equals mg divided by cosine theta.
Yeah. So we would add the mg to both sides, and then we would divide by the cosine. So we're going to have n equals mg over cosine of theta. Are we all hanging in there right now? Are we good? Yeah? Awesome. Okay. So now that we have that, what do we want to do? I mean, yeah, if we want to just go ahead and solve for n, we can. You guys just want to go ahead and solve for n? Okay. So if we solve for n, what's our mass? It's still 1,500. You guys are so smart. Yep, it's the same car. So our mass is going to be 1,500 kilograms. What's g? Yep, 9.8 meters per second squared. And then cosine of what? 15. Okay, what is our normal force equal to?
15,218.56.
Okay, can you say that again?
15,218.56.
Did anybody else get that? Because when I did this, I didn't solve for n. I just plugged this whole thing.
Yeah, it's the same thing right there.
Yeah, you guys got the same thing? Okay. Because I just took this whole like little function and plugged it in to this one. Because you guys, that's what we're going to do now. We're going to take this information for n that we just found, and we're going to plug it into this top equation. Because we're looking for v, right? That's what we were asked to find. Yeah? So now we know n, we know theta, we know m, we know r. Our only unknown is what we were asked to find. Does that make sense to everybody? Okay, so what we want to do is we're going to take this equation right here. And if you guys just don't want to look at this, you can do that. And we need to rearrange it to solve for v. Okay? How are we going to solve for v? What do we need to do with this n sine theta equals m times v squared over r?
Multiply by the r on both sides, and then divide by n. And then take the square.
Okay, so we're multiplying by r on both sides?
Yeah.
So we're going to have r n sine theta equals mv squared. Okay, now what are we doing?
Divide by the n.
Divide by the m? Okay. And then what's the final thing we got to do?
Take the square root on both sides.
Yeah, take the square root on both sides. So we've got this. Now can we plug in to solve for our v? Yeah. Okay. So we are going to have the square root of what's our r?
17.
Okay. And then we solve for our n, right? So we can plug it in straight forward. And then sine of what's our theta?
15.
Okay, divided by our mass, which is the 1,500 kilograms. So what do we get as the velocity that we would need to be going at in order to keep our car moving without friction?
5.6
You said 13.56?
Yeah.
Okay. If you look at my work, you're going to see that I got an answer of around like 14.5 but that would be that rounded. So I probably just rounded my answer. Okay? That good with everybody? Yes.
How do we know that for when we're doing like summation of F and or F and FC? How do we know to use like N sign?
Oh, this is an R. This is a Z.
How do we know to use N sign theta?
Yeah, so like how is R sine, like in sine theta of R?
Okay, who can explain it to them? Because you guys told me to use sine and cosine.
Because like,
So remember, okay, so sine
because R is that x-plane on that chart.
is opposite over hypotenuse, right? And cosine is going to be adjacent over hypotenuse. So what you need to think about is where is your 15 degrees at in respect to this end? Is it going to be here or here? Because remember, that 15 degrees is right here. So where's it going to repeat itself? Is it going to be attached to the R axis or to the Z axis?
So this is gonna be to the right of the.
Yeah. So do you see how that's the adjacent to the angle?
I see what you-
Okay. Yeah, does everybody see that? It's adjacent. And then when you're looking for the R component, what is it?
opposite.
Opposite to the angle, okay? So that's how we pick the sine and the cosine. Yes.
If you start from 0, like if you start from 0 in reference to all your angles, so this one say is 15 degrees away from the like the y-axis traditionally, and so you add that to 90 degrees and you'll get like 105, right?
Mhm.
Is it possible to just use like cosine always for the x component and sine always for the y component? If you like convert them over to their like angles.
So if you wanted to use cosine for the x component here, what I would suggest would be even easier is just doing 90 minus 15 to get that theta.
Yeah. It's just confusing when you use like sine for like the x-axis.
Yeah, but you've got to remember that for my regular physics class, I make their problems easy so they always have cosine x and always have sine y. You guys are AP and you're calculus based. So what they care about is they want to know that you actually know what these mean. This does not mean y. This does not mean x. It means adjacent and opposite. So like if I always keep cosine x and sine y in class, and then you get to the AP exam, you're not getting that. And then you're going to be confused, and then you might not do very well, okay? So you've got to think about those functions for what they truly mean. And I know it's not your fault that you can't do that, because in math class you guys get taught cosine is x, sine is y. But that's not how it really is, if that makes sense. Okay. I'll step down off my soapbox. Yes.
N R equals N sine theta. Is that like a known formula, or did we get that?
You got that. Because you see how n is in both the r and the z axis? Okay? So usually it would just be on the z axis if we were on flat surface. But since the road is banked, now it's pointing off into both. So you guys derived that the portion of the normal force that would be in the r axis would be in sine of this angle, because that's going to give you the r. And you derived that the z part would be in cosine, because that's what's going to give you that z portion.
And then how did we know to set like N sine theta equal to N v squared r?
Oh, because F always is equal to, like, a force is always equal to mass times acceleration. And guys, remember, we always said that which way does the acceleration point when we do circular motion?
Towards the radius.
It always points along the radius towards the center of the circle, which means that acceleration always has to be on that r axis.
So then why do you subtract it for the z?
Okay, we're subtracting the force of gravity. Because it's pointing down.
Because we're going to net force.
Okay.
Any more questions? No? Okay. Yeah, I know yesterday was so much fun, but I warned you guys. That circular motion could get messy. It's when those angles get added in. Angles always make everything worse, right?
So this isn't three-dimensional motion yet, is it?
I mean, technically it is, yeah, because we have the RTZ. So we do have one that's coming out at us. So that is 3 dimensions in our coordinate plane. Okay, let me see what time you guys get out of here. Okay, we're good. So I had one more example I wanted to do with you guys before I let you start your problem set, which there's a chance that might become just homework for tonight, but it's only like 7 problems. So it's not completely insane because we're going to start circular orbits tomorrow because we're on you guys are here every day now. So we got to get moving to get ready for that AP exam. All right. So this one is about a rock in a sling. Have you guys ever had a rock and you've like flung it around and yeah, that's dangerous. Don't do that. Okay. So we've got a Stone Age hunter. All right. And he is going to place a 1 kilogram rock in a sling and swing it in a horizontal circle around his head on a 1 meter long vine. If the vine breaks at a tension of 200 newtons, what is the maximum angular speed in RPM with which he can sling the rock? Okay, so let's start with a picture. He's like really putting his back into it, you guys. All right, so he has this rock attached to a sling. And oh my gosh, oh no, there's an angle. Okay.
It's horizontal.
Yes, but have you ever swung something around? Does it ever go perfectly horizontal? No, there's always some slight angle. And you guys are AP, so have fun.
It doesn't ever get.
Yeah, it never gets perfectly straight. Okay, so let's see. The rock is our object, right? We've got 2 forces acting on it. What are they?
Gravity.
Yep, tension and gravity. Force of gravity and tension. Okay, that's what we got acting on it. And let's list out those knowns. Okay, we know that the mass of the rock is 1 kilogram. We know that the length of the string is 1.0 meters. Since there's a theta, is that the radius? No, okay. And we know that the maximum tension that this can take is, yeah, it's going to be 200 newtons. And what we're asked to find is that maximum angular velocity in RPMs. Okay? So this is what we're dealing with. All right. Just to keep us on our feet so we know what's going on. I'm going to have these labeled again, Z and R. So, what axes do we have forces in? Z and R, okay. So that means we're going to have to sum the forces and the R, and we're going to have to sum the forces and the Z. So look at this, look at these 2 pictures hard, okay? To think about if R is cosine or sine and if Z is cosine or sine.
We're going to use cosine for R.
Yes, why are we using cosine for R?
Because the angle is going to be
Mm-hmm. It is. You see how the angle is basically, it's going to be touching that R now? Okay? So that means that up here, we have T cosine of theta. Is there anything else in the R-axis? No. Okay. Which means that, remember, it's always equal to MA, right? And we know that A of R is the only one that actually has acceleration, correct? Because the other two planes have acceleration equal to 0. So that means it's going to be equal to M V squared over R. So that's our R plane, okay? Now what do we have in the Z plane?
T sine theta and minus mg.
Yep. And what's that going to equal? 0, because there's no acceleration in the Z plane.
Do you have an F net here?
Yes, we do have an F net. Where do you think it's pointing?
Towards the left.
Mm-hmm. Which towards the center of the circle, you guys, is always considered positive. Okay? Because the center of the circle is always positive. So I noticed something in both of these that we really need. What do you guys notice? Theta. We really need theta, right? Like we really need theta. Okay, so top or bottom, which one do you think we need to use to solve for theta? Bottom. Why do we have to use the bottom? Yeah, we don't have velocity. We also don't have R, okay? And because it's set equal to 0, which always makes our lives easier. So if we take this and we say T sine theta minus mg equals 0, what do we need to do to solve for theta?
It's going to be inverse sine of mg divided by t.
Does everybody agree with that? Do you want me to show you how we got there? Yeah, let's show how we got there. So T sine theta equals mg. So we added mg to both sides, okay? Then we're going to want to divide both sides by t. So we'll end up with sine theta equals mg divided by t. And then how we get theta by itself is we do the inverse sine. So we end up with that theta is the inverse sine of mg over t.
What's the inverse sign? It's just
Which is the opposite of sine.
It's the same as dividing by sine. Yeah. Okay, so do we have everything we need to plug in? Yes, we do. So the inverse sine of our mass of 1 kilogram times what's G? 9.8 meters per second squared divided by our tension, which what's our maximum tension?
200 newtons.
200 newtons. Okay, so what is our theta? 2 point what?
2.081.
0.
I got 2.81.
2.81.
Okay.
I just read that.
Oh, I was like stressing. I was like, oh no. Okay, so 2.81. All right, now, since we have that, are we able to solve for our velocity? Why? Yeah, we can, because we're going to figure out how to solve for R. Okay? We're going to say how R is represented. How do you guys think R is represented in terms of L and theta?
It's the hypotenuse.
Yeah, we're going to do L. You think cosine or sine theta?
Both.
Okay, so we said the theta is like basically sitting right here, right? Okay, so how do we find the radius?
Cosine of theta.
Yeah, we're going to take the length of this L, okay, in order to find R. We take the length of the string L, cosine theta.
Wait, so if it's at an angle, then why are we only using cosine?
Because we only need r, we don't need z.
But isn't it the hypotenuse, which is the length of the string, so
We have the hypotenuse there, where it's included.
it doesn't give us the length of the hypotenuse though, so that's.
We don't want the length of the hypotenuse. We already have the length of the hypotenuse. The length of the hypotenuse is 1.
Isn't that the length of the string though?
That is the length of the string, yeah. So we have to use the reference of the length of the string in order to figure out what the radius of the circle is.
Exactly, so if the length of the string would equal the radius.
No, because there's an angle. So like if I have a string, and let's say it's like a foot long, but I'm spinning it at an angle, the radius is not necessarily going to be a foot. The radius could be super small.
Ian, think about this. You can have a 1 meter
Okay,
long string.
let's look at
You
you're
can
at
barely
Tony
spin.
Pepperoni's pizza shop, right? You get a pizza dough has a foot long radius, and you're spinning it in the air, but it kind of turns on the side. The pizza total is still like 1 foot radius.
Yes, but the radius of the circle that it's creating in the air is not.
So we're looking at
We're focusing on the circle that is getting formed in the air that this rock is going around. The rock is our particle. So let's say, hold on. If you're holding it and you have it at an angle,
Wait, so it's not like a perfect.
no, I've said that a million times. That's why it's at an angle.
But if it's a sling, it's gonna be.
No, it's not. You can never get it to be perfectly horizontal if you are slinging it around. It will always be at some sort of angle. Always. No matter how perfect you think you are, Ian. It's never going to be perfectly straight. Go home and try it with something. I don't really have anything to tie up right now to anything, but like, let's say I take this. Okay, here. Let me start slinging it. It's at an angle.
That looks pretty.
It's not straight. There is an angle there.
Yeah, very fine. Looks straight to me.
It's not though. There is an angle.
Okay, think about the angle.
Okay, I get it.
Okay? There is an angle when I am slinging this. So the circle that my keys are traveling around is not the length of this. It's going to be slightly different. Okay? Yes, Donald.
So this is back to the cosine sine thing. So whenever you say you want to find the horizontal aspect of it, so depending on the angle, say the angle was say you're saying the angle in reference to the top of the y-axis, you would depending on which depending on whether or not you're trying to find the x or y-axis, you would see which one, which of the first letters. So say cosine is adjacent over hypotenuse. So it equals what you get from cosine will equal the adjacent, and then sine is opposite over hypotenuse, and what you get will equal the opposite.
So what happened right here with this is that we said, okay, cosine of theta is equal to the adjacent over the hypotenuse, which means it's r over what we know the hypotenuse is to be L.
Okay.
So to find r, we take that hypotenuse L
Okay.
and we multiply it over.
That makes sense.
I get it now.
Okay, I'm sorry. I thought when you guys told me to use cosine, it meant that you knew what happened. Especially when I said we multiplied it by the hypotenuse. But it's okay, because do we really understand now, though? Because I can keep talking.
No, I'm good.
We're good?
Yeah.
Okay. So, if we now know what r is equivalent to, and we know what theta is, can we now solve for v?
Yes.
Yes, okay. So we're going to take this equation right here. We're going to take this t cosine theta equals m v squared over r. How do we rearrange to solve for v? What do we do? What's the first thing we do, you guys?
You do, all right, so it's going to be t cosine theta times r divided by m. It's gonna be the square root of that.
Does everybody see that? That's what Ian said, okay? So now we need to plug everything in. So R, we know, is going to be 1 meter times cosine of what's our theta?
2.81.
Okay. And then we're going to have T. What's T? What's our T? 200 newtons. And then cosine of, once again, what's our theta?
2.81.
Divided by our mass. What's our mass? Okay. Let me know when you got the answer.
Okay, I got 14.13 meters per second.
Yep. Are we done now?
Nope. No, we have to find the, no, we don't.
Yeah, we need the angular velocity. Okay. So, who remembers what it is? What's our equation?
Is it V over R?
Yep, it is. It's V over R. Okay. So, what's our V? Huh?
14.13.
Okay. And R is represented by, once again, remember, 1 cosine of 2.81. So, what's omega equal to?
14.14.
Ooh. What are the units on that?
That's stupid. It's
Yeah.
1.5. That's 1.5.
Yeah,
So
so-
1.5.
Radians per second.
It rounds it to 14.15.
Wow, Donald.
I hate you, dog.
Yeah, 60.
How dare you disrespect me like that?
60?
Okay.
So you don't use 60.
If you want to skip a step and just use.
Now, is that the answer?
Yeah.
No, it wants RPMs.
Oh my god. 14.15 RPM.
14.15 radians occur in 1 second. Okay. How many radians are in 1 revolution?
2 pi.
Okay. How many seconds are in 1 minute?
60.
Wow, I'm so impressed right now. Okay. So what's our real answer?
Okay, that's right. $135.
135 what?
1.
Well, I mean, like, what are the units?
135.1 revolutions per second.
Minute. Minute. Bam, there we go.